right, in our last video we were talking about directly proportional. So now we're getting towards the end of the semester, and we're doing a lot of applications. So now we're going to give you, in this particular video, we're going to give you the gas equations and the gas laws. How gases, how they react, and where they're directly proportional, and the formulas that we use to calculate them. So I'm going to give you all of the different equations and gas laws at this time, and then we're going to come back and do a big practice deal on application. So first of all, there's Boyle's law, okay, and Boyle's equation. Boyle's equation says PV is equal to K, where P is pressure, okay, P is pressure, okay, V is volume, and K is a gas constant. So what happens is pressure and volume is equal to the gas constant. So the question that we ask ourselves is, what two factors are directly proportional in Boyle's equation? And it's pressure and volume. So if I know the pressure and I know the constant, then I can calculate the volume. If I know the volume and I know the constant, I can calculate the pressure. If I know the pressure and the volume, I can determine the constant. So I want to know in a tire, okay, I want to know how much pressure it's going to take and how much volume it's going to take to blow up this tire, so I know what the constant should be when the tire is at 33 pounds of pressure, or whatever it is. So that's Boyle's equation. Pressure and volume is equal to the constant. Then we have Charles' equation. V1 over T1 is equal to V2 over T2, where V is volume, T is temperature. Now, V1, okay, V1 is the initial volume, okay, and V2 is the final volume, okay. So in Charles' law, we've got a temperature change or a volume change, okay. So what's directly proportional? Volume and temperature. Oh, well, this is pretty cool, because let's use our same example as a tire, okay? I want to know how big the tire is going to be, okay? Here's the initial tire. The temperature outside is 70 degrees. Here's the volume of the tire. Oh, that's pretty good. Well, it's directly proportional. So what happens if the temperature goes to be 100 degrees or 120 degrees, or the road is 150 degrees? What's the volume of that tire? So then I can calculate, before I ever even blow that tire up and see how big it's going to be, I calculate what the volume is, and I know how big that tire can be before it blows out. So once again, a lot of applications, okay? But Charles' law, V1 T1 is equal to V2 T2. Now, let's move on to the next one, okay? The combined gas law, okay? The combined gas law, P1 V1 over T1, all of the initials. The initial pressure, P is for pressure, V is for volume, T is for temperature. The initial pressure times the initial volume divided by the initial temperature, okay, P1, V1, T1, is equal to the final pressure, P2, the final volume, V2, divided by the final temperature, T2. So P1, V1 over T1 is equal to P2, V2 over T2. Now, what's directly proportional? Oh, the pressure, the volume, and the temperature. How cool is that, that gases are all directly proportional to temperature and volume and pressure? Okay, so if I say what three things are directly proportional, in this one we know all three. So we can calculate, even if we want to know the temperature inside the tire, we can calculate the final temperature. We can calculate the initial temperature. Anything in this equation we can algebraically go and solve for. So that's pretty cool. Then we have the ideal gas law. PV, pressure and volume, is equal to nRT, okay? Now, the key is that N is equal to the number of moles. N is the number of moles. R is a gas constant. R is a gas constant. All right, and T is temperature. So, anytime we're dealing with a problem and it says, how many moles of the gas are there? Okay, or it says you have so many moles of gas. We'll always use the ideal gas law anytime we see something relating to the number of moles. PV equals nRT. All right? Now, we talked a little bit also about the barometric pressure, about all the gases exerted down on the mercury barometer and how it brought it out, and how we have atmospheric pressure on us all the time. Well, Dalton's law of partial pressures says the pressure of each gas, P of 1, P of 2, P of 3, and it could be P of 4, P of 5, depending on how many gases you have. The sum of all the pressures equals the total pressure. Now, what's a metric unit for gas pressure? It's a kilopascals. So the symbol for that, K for kilo, and then PA for pascals. So kPa, kilopascals. And we talked a little bit in our last video about kinetic energy of molecules. When the molecules stop moving, then we have absolute zero. That's the temperature at which molecules stop moving. Doesn't happen very often. Even in solids, molecules are always moving. So we'll come back and talk about this a little bit later. These are all big things as we get ready for looking at all of the gas equations. Now, we'll transfer over into the applications for this in the next video, and we'll do problems and applications, and we'll apply all these. So once again, this is simply a list of all the different gas equations. So depending on what we know we can use, we have Boyle's equation, PV equals K. Charles' equation, B1 T1 is equal to B2 T2. So once again, we have initial volume, initial temperature is equal to final volume, final temperature. Combined gas law, P1 V1 is equal to T1. P1 V1 divided by T1 is equal to P2 V2 over T2. And then the ideal gas law, we hone in right away whenever we see something with moles, PV equals nRT. And then Dalton's law of partial pressures, we won't use that to calculate a lot of problems, but it is simply the sum of all the pressures equals the total pressure. So that's a basic introduction, gives you all the possible gas laws, gas equations that you can choose, and we'll do another video on applications. So until then, we'll see you then.